In this lecture, we will continue our discussion with the Avrami equation, and we will look at how to experimentally verify the Avrami equation. So, today's lecture will be focused on experimental verification of Avrami equation. Which is, let me just write the equation as well here, f is equal to 1 minus e to power minus k t to power n. Now, in order to experimentally verify such an equation, we have to conduct some experiments on a material in which we can measure for a given temperature amount transformed from one phase to another phase in different times. So, for example, one can take a sample of steel in which we could look at the amount of perlite transformed as a function of time from the austenite phase at different temperatures. So, for each temperature, one should be able to determine the parameters of the Avrami equation n and k. So, but just before we go into this discussion, let us quickly have a look at the iron carbon diagram. So, and if one looks at the iron carbon diagram, this is the iron carbon diagram here. Here you can see that you have, this is the usual iron carbon diagram which you already know. You are, let us say, a steel with a certain composition is heated into the austenite field, and then it is allowed to cool down to produce the parent to produce the product phase alpha ferrite plus Fe3C cementite, which together are called perlite. And depending on the carbon content of the steel, you may form pro-eutectoid ferrite, you may form pro-eutectoid cementite, or you may produce directly 100% perlite. So, let us quickly see what kind of microstructures we get. For instance, if I take a hypoeutectoid composition, which is given by this broken line, I take the steel to in the austenite range and then cool down, then the microstructure evolved. If I look at through the optical microscope, this is what kind of microstructure one would see, that you have a matrix which is essentially ferrite, and there are darkish regions, as you can see, which if I zoom into one of these regions and look at the structure under a scanning electron microscope, then this is what I am going to see. I am going to see these layers, these are the layers of ferrite and cementite, or what is together constitutes perlite, is the result of the eutectoid transformation of austenite to perlite. To see these layers even more clearly, one can further zoom into this and look at it under an atomic force microscope, and you can see these layers very clearly. And just to put things in perspective regarding the dimensions, this length is of the order of 500 nanometers. So, you can see that thickness of each of these layers is of the order of less than 100 nanometers. Similarly, if I take a hypereutectoid composition given by this broken line, which is now greater than the eutectoid composition of around 0.8, and look at the microstructure in an optical microscope or in a scanning electron microscope for better resolution, one can see that there is a network of phase precipitated. This is the cementite phase, the pro-eutectoid cementite that forms, and this cementite is essentially heterogeneously nucleated at the grain boundaries. When the temperature reaches below the eutectoid temperature, then the remaining austenite transforms to perlite. So, all of this regions within that is all perlite. Now, consider a third composition, and that is the composition, the eutectoid composition. Now, in this composition, if I let it cool from the austenite, I will get now a structure which is 100% perlite. Now, this is the in fact, this is the material I am interested in doing an experimental verification of the Avrami relationship. So, what we can do? Well, we can take a eutectoid sample, heat it to the austenite region, let us say heat it to about 900 degrees centigrade. So, we will be well inside the austenite region, and then quench it at a certain temperature. For instance, one can quench at 700 degrees centigrade. Now, how does one quench at 700 degrees centigrade? It is easy to quench in water when we want to produce martensite. Well, you take a salt bath. A salt bath is a furnace in which a certain composition of different salts are taken, so that they have a certain range of melting point. So, we quench in a molten salt bath. So, if a salt bath is kept at 700 degrees centigrade, then we will quench the sample at 700. One sample we quench, keep it for some time, take it out, and then quench in water. So, what will happen? The final structure that will form would be some amount of perlite which has formed depending on how much time the sample has been kept in the salt bath. The remaining austenite transforms to martensite on water quenching. Now, we do a metallography of this sample. We take it to a microscope. We first of course polish and etch to reveal both the perlite and the martensite, and then measure the volume fraction of perlite in the sample. Now, how does one measure the volume fraction of perlite in the sample? Well, we take a sample. For instance, let me illustrate this on the board, that I am looking at a microstructure which has some perlitic regions. So, I am just drawing a schematic sketch, and rest all is martensite in this. So, we use a metallography technique called point counting. In this technique, one would place a grid of points. So, a grid is something like this, where you can see lines, horizontal lines and vertical lines in the grid. These are the intersection points. All of wherever the lines are intersecting, these are the points of intersection. We count how many such points are in the perlitic region. Suppose there are n points inside perlite, and there are total of capital N number of points in the grid. Then the volume fraction of perlite that is formed is given by this estimate or this ratio small n upon capital N. This is a well established technique for measuring volume fractions. Now, you would not just do it in one area, you would do it in several areas and then find a average volume fraction, and that would be the representative fraction of perlite formed. Now, this you would do on one sample one time, a second sample different time, and so on until you get a values of volume fraction and time. So, I will get a table in the end that at time t1, and this is all done at some temperature T. T1, F1, T2, F2 and so on, the nth point. So, if I have n number of samples, I will have n data points. Now, this data needs to be analyzed using the Avrami relation. So, now the next thing we need to look at is how do we analyze this data. So, let us first see what do we mean by analysis, and let me show you here that we want to analyze Avrami kinetics, which means we need to analyze the experimental data that we have collected. So, suppose, and this is an experiment in which some data has been collected of austenite to pearlite transformation in a eutectoid steel. So, and this temperature here, though it is not mentioned, the temperature of the salt bath was kept at 660 degrees centigrade. So, at 90 seconds 0.01 only 0.01 has transformed, or 0.01 fraction is the pearlite phase, or simply 1% pearlite has formed. At 180 seconds 0.2 or 20% pearlite is formed. 225 seconds you have 48%, 240 seconds you have 78%, and at 300 seconds almost we are now very close to 100% transformation. Now, the first thing you do whenever you have some experimental data, the best thing you can do to begin with, if you have no clue, is to simply plot it on a graph sheet. And this is let us say the graph that you get of this data which has been plotted here. Of the vertical axis is the fraction transformed and the horizontal axis is time in seconds, and this is the data point that you have. From this you may start making some conclusions. Now, the objective here is, if we need to analyze this data in terms of the Avrami relation, I need to find the parameters n and k, and once I know what the parameters n and k are, I would be of the Avrami equation here, I would then be able to plot a continuous graph superimposing on these points as shown here. So, this is what I am after, that once I find n and k, then I can plot a continuous graph through these set of points, and I can now predict what would be the amount transformed at different times for the given temperature. So, now the next objective is that this how to go ahead to look at this problem, and to look at this problem, let me just go back to the board again and look at this Avrami equation again and see what we can do with this equation. Many times when you have a nonlinear equation like this, you try to see if one can linearize this equation. So, in order to linearize this equation, let us rearrange this equation in this fashion: 1 minus f equals e to power minus k t to power n, and then take logs on both sides and take the log of this, and taking the log of this would be equivalent to writing this term as minus k t to power n. Now, what I do is bring this negative sign on this side. So, I have a relation like this. Take logs again of the left hand side minus ln 1 minus f and the right hand side k t to power n, and I will get a relation log of minus log 1 minus f. Now, bringing the negative sign here ensures, since f is less than 1, log of 1 minus f will be a negative value, and the negative sign here will make it positive. So, I will be able to take the log of a positive quantity, and out here if I take the log of this, this will simply become ln k plus n ln t. Now, you can see that the left hand side term taken as a whole linearly varies with log t. So, this is what we mean by linearization, and let us go to a spreadsheet, take this data that we have and plot it on a graph and see how that graph looks like. So, here I have that same data of isothermal transformation of austenite to pearlite in a eutectoid steel at a temperature of 660 degrees centigrade, and let us take logs on both sides. First take log t that I need to calculate on the right hand side of the equation that I have. In fact, let me show you this equation as well, so that is also in front of us. So, I want to calculate the left hand side and the right hand side, which is log t, and the left hand side, which is our 2 logs. So, let me calculate the right hand side. So, let us call that as, spreadsheet has a function called natural log ln, and it requires me to give time here, which is in cell A5, and this gives me the value of log 90 here. And here let me take logs minus log. So, I have to take 2 logs and then I to take 1 minus f, and therefore, this in cell B5 is f, 1 bracket closed, second bracket closed, and this gives me the left hand side term for at time t equal to 90 seconds. Let me just put another bracket here, that is all. Now, copy these 2 formulae downwards and calculate for each of these experimental data points. I get a set of values for log t and log of minus log of 1 minus f. Now, this here will show me the result if I plot this data. Now, this data shows that now the points appear to fall on a straight line, all the 5 points are roughly on a straight line. Obviously, when you do an experiment, there are going to be fluctuations, so they will never fall exactly on the curve. Now, one thing I can do is, now I can try to draw a straight line through it, but how do I draw a straight line through it? One is I can use my judgment and make a plot. So, I could have a line like this, but somebody else may draw a line like this, or a third person may draw a line like this who thinks that this line is better. So, who's to figure out that which is the correct line? So, what we should try to do now is how to objectively find the best line passing through this set of data points. Once we know the best line, then the slope of this line then would be the value of the parameter n of the Avrami equation, and if we extend this line all the way until it intersects the vertical axis, that would give me the intercept, and intercept would then be nothing but log k. So, finding the best line essentially involves finding out the intercept and the slope of the two and then from that I get my Avrami parameter. So, I have to, my problem at hand now is, what is the what is the best so called best values of the coefficients n and k. So, we would then I will now I'm going to do I'm going to digress a little bit, and we will look at how to find the best fit parameters of the Avrami equation, or how to find the best fit parameters for a straight line if I have a set of data points. So, what we do is we have already linearized this equation. Let me call the left hand side as simply y, right hand side log t, let me call it as x, log k, which is the intercept, let me call it a0, and let me call n as a1, so that I have a simple form of the linear equation y equals a0 plus a1x. So, if I have a pair of points, a set of pair of points x and y, then given these set of data points I have, I want to find the best fit parameters a0 and a1, which would give me the best fit line through the experimental data. I will discuss how to determine the best fit parameters a0 and a1 through the method of linear regression in the next lecture.